Hello everyone and welcome back to your YouTube channel and welcome to this video today. And the job today is a very practical work related to state space model representation. In fact, today what we are doing is basically derivating the state space model representation for a very simple controller used in electrical power system. Specifically, we are using a excitation system as the example for the video today. So without further delay, let me start with the simple and general information. Remember, as usual, you can go to my ResearchGate repository, and inside the ResearchGate repository, you will be able to find the slides and scientific papers and many others documents that they can support you. Also, many of the practical examples of these videos are located in my GitHub repository. You can go there and you can get more information. Also, if you are watching this video, it's because you are in YouTube. And if you are there, please feel free to subscribe if you like the videos and also leave a comment over there. If you want to follow what we are doing, please go to our social media, specifically Twitter and LinkedIn. And finally, some people ask me to put over there my email, and you can drop an email directly. Well, what is the agenda for today? Well, today we have a very short agenda, however, is very intensive in terms of calculation. And the agenda will start with the first section, that is basically the motivation and inspiration for this very specific video. Then I will show you the state space representation. The state space representation is quite frequently used for modal analysis of linear dynamic systems. And in power system, we use that for a small signal stability. However, this is not a video about small signal stability, or this is not a video related to eigenvalues, okay? However, the job today is taking this beautiful excitation system that we have here, and we want to move from the block diagram representation into this amazing state space representation. And in simple words, what we want to do is to obtain the matrices A, B, C, and D in terms of the characteristic of this block diagram. Well, let's move to the next section, and right now it's time to talk about the motivation. And the starting point here is that in many cases we need to have the mathematical description, the mathematical model of a dynamic system. And one of the most used representation for dynamic system is what we call the state model representation. The state space representation. And as you can see here, equation 1 and 2, basically equation 1 is a differential equation that is basically representing the dynamic of the system. And this is a set of first order differential equations. And over here we have a set of algebraic equations. So the combination of equation 1 and 2 is what we call the state space representation, where x, this beautiful letter x over there, is a vector that is containing the end states in the system. And the matrices A, B, Z, and D, they are basically matrices that represent the characteristic of the system, and Y and U represent the output vector and the input disturbance respectively. Why the state space representation is quite used? Because in many power system analysis, like the model analysis, this representation can be used to describe the performance, the dynamic performance of the system. In reality, the state matrix, the matrix A, is quite used for small signal stability because basically the eigenvalues of the state matrix representation is what we define the oscillation or the modes of the system. So what you need to understand is that this representation, the matrices A, B, C, and D, they are quite useful in many fields of power system, but also in control system. However, what is the motivation for today? Well, I need to run a practical example, and this practical example require a test system. And in this case, we are going to one of the most famous books for power system dynamics in terms of a small signal. And this is the book of Graham Rogers. It's a book coming from 2000, and the name or the title is Power System Oscillations. Specifically, chapter number 3. Chapter number 3 is quite popular. The chapter number 3 is quite popular because it's basically the chapter dedicated to modal analysis of power system. And inside that chapter, there is a very simple example. You can go there and see more details. And you can see the very interesting block diagram that we have in front of us. That block diagram, Graham Rogers said that is coming from a simple excitation system. To be honest, it's one of the most simple, I will say simplified or the simplest excitation system that you can find. As you can see, the representation over here is Laplace transformation. We are using transfer functions for each block, and we are using signal flows to represent the system. The first block over here, you can see with the number 1 over here, is basically representing the voltage transducer. That means that the input here, the terminal voltage, is going into this block, and the idea is to convert this measurement, okay? And this block is basically a first order transfer function with a time constant TR. And this is what we call a lag controller. Regarding the block number 2 is what we recognize. The block number 2 is what we recognize in a excitation system as the exciter power amplifier. And this is basically, again, a first order transfer function with a gain K at the numerator of this transfer function. And this is what we call a lag controller again. Then we have the core of this excitation system, that is the transient gain reduction, that is the block number 3, and this is a beautiful LED lag controller. Finally, we have block number 4, that is the feedback, and over there you can see the name is transient output feedback, and that is the final block to describe this closed loop controller that represents the excitation system. Now, what is the idea? The idea here is that if we want the full state representation of this system, what we need to do is identify the differential algebraic representation, the time domain representation of each one of those blocks. If we have the differential equations and algebraic equation representing each one of them, then we can combine all of them in order to get the full state space model representation for this excitation system. And that is what we will do. Each one of these models, total of 4, we are dealing with them and creating the representation. And let me move forward right now. Let's start with the first block. The first block is located at the input where the measurement, the voltage, terminal voltage measurement is coming in, and that is what we call the voltage transducer. And in this case, you must remember, this is a first order transfer function, but that is what we call a lag compensator. The name lag compensator must be familiar for some of you. It's coming from control, And they are very interesting characteristics that they make attractive for power system. The first thing is that these control allow the use of high gain, low frequencies, and that improve the steady state error. To be honest, that is one of the most important characteristics of the lag compensators, that in the time domain, they allow the reduction of the steady state error, but also they allow to reduce the gain at the crossover frequency. Also, those compensators, they have the possibility of reduce high frequency gain of the system, so that allow the attenuation of noise. Noise attenuation is very interesting, it's quite important, especially for this application, for this exciting system, because we need to reduce the noise coming from the measurements, in this case, the terminal voltage. So this is one of the representation, and on the right-hand side, we have the second representation of the transfer function of this controller. Typically, there is a 0 and a pole, and you can see over here that t is the time constant and beta is a gain. Both of those numbers should be positive, and that is the realization, okay? However, lag compensator is one of the compensators that we use in control, because also we have the LED compensator. What is the difference between lag and LED? Well, the lag compensator is basically a controller that is dominated by the performance of the pole. So that is the classical representation of a proportional integral controller, or PI. However, on the other hand, we have the LED controller. In the LED controller, the 0 is dominating the behavior. So in those controllers, they try to act faster, and that is the reason that we use proportional differential controller. So they are very different, the lag and the LED compensators. However, the good idea is combining them, and we will do that in few slides in this model, okay? But now, what is the practical job that we need to do here? Well, what we need to do is basically take the block number 1, that is the voltage transducer, and transform or convert that first order transfer function into a most, let's say, simplified version. What we need to do is basically eliminating the first order transfer function and converting that into very simple integrators. So when we look here into the block number 1, there are two options. One realization that I put here the name realization 1 and the realization 2. What I am trying to tell you is that I am converting a complex first order transfer function into a simplified version that is basically integrators in a closed loop model. As you can see, those two realizations, they are similar. The main difference is the location of the feedback point. So what we need to do is basically, using those two realizations, obtain the time domain equations, or the differential algebraic model. And that is extremely simple, because it's just playing with the block diagram and the flow signals, and just basically obtaining the equations. So what you need to do here is, first equation, you can see that the output is y is equal to x, and that is the algebraic equation. And the second equation is quite simple, because what we want to obtain is, here the input is u, the feedback is x, and here there is an integrator. That means that what we are getting over here is x dot, or the first derivative of the state equation. And this is again, so what we are obtaining here is basically x dot multiplied by t. So if we look this equation from this addition point, we will have u minus x is equal t multiplied by x dot. And extracting from here x dot will be basically u divided by t minus x divided by t. So you can see over here we have now we obtain here the differential equation. For the future future blocks, you can do this by yourself, but here let me go to the realization number 2. Realization number 2 is quite simple. Again, the algebraic one is the easier one. You can see that the output is input multiplied by the gain transfer function, and we obtain here the first algebraic equation. And then at home, you can do the second equation, that is basically the differential equation, okay? Again, the job here is taking one of those blocks and converting those blocks into the simplest model that is basically integrators and closed loop controllers, okay? Now, let me go for the next block. The block number 2 is basically, again, a lagged block. That is basically the exciter power amplifier. As you can see, it's located at the output of this controller. And what we need to do is convert this block from the Laplace domain into the time domain. And over here, you can see that I am presenting for you the equations again. You can use realization 1 and 2 and make the modification from the previous slides, and you will get those two time domain representation, okay? Then probably the most interesting block is the block number 3, because the block number 3 is a leg lag compensator. And the leg lag compensator, to be honest, the leg lag compensator is quite interesting, because the leg lag compensator, what it's doing is basically combining the best properties from the both compensator. The LED compensator, they try to increase stability and speed response, and the lag compensator, they try to reduce the steady state error. So by combining those two control actions, those two compensators, we can control the time domain and the frequency response of the system. So that is the reason that the leg lag compensator is quite used in many control systems, okay? But coming back to our example, what we need to do is to take this block number 3, and convert it into integrators. Again, what we need to do is use the basic mathematics, and from here, what we need to do is from this very simplified state space model for the leg lag compensator, write the equations over here and the differential equations in the time domain, and we obtain the differential algebraic model that we will use for the final state space representation. Now, let me go to the final block. Over here, you can see this is the transient feedback block that is located at the feedback of this exciter. And what we need to do again, this is the block number 4. This number should be here. But the block number 4 can be converted into this block diagram over there. And now it's time to write the equations of that simplified model. Writing the model, you can see over there, we obtain the differential algebraic equations, and now we have complete the representation using using the model for each one of the block. Now we need to combine those models. So now what we want to do is the complete state space model. And to do that, what we want to do is create the equations that they are located over here. This is equation 1, and this is equation 2. We want to create the differential algebraic model using the state space representation. For each one of the blocks, if there is an integrator inside the block, we will have one state variable. I repeat again, for each one of these blocks, if inside the block there is an integrator, we will have one state variable. So in this model, we have 1, 2, 3, and 4 state variable. That is the reason that the state vector has 4 components, and those 4 components represent the 4 different states in this system. Regarding the inputs, it's very clear. We have one input, that is the terminal voltage coming from measurements. We have the reference voltage, and that is the reason that the input vector has 2 components. And as usual, you can see this is a single output system, and the output is just the voltage of the field winding. So here we have the formal definition of the structure of the model, state model of this excitation system. And what we need to do now is basically obtain the 4 different matrices A, B, Z, and D. And to obtain A, B, Z, and D, what we will do is use the models that we obtained in the previous sections. And if you look over here, let me move to the next slide. Here in the next slide, you can see at the middle or the center of this slide, we have the original system. And what we have done is create a simplified version using integrators for the block number 1, for the block number 2, number 3, and number 4. And when we complete those simplified models, the next step is, well, let me show you the time domain representation, the differential algebraic representation. So what I am telling you is, again, here in the middle, we have the block diagram, but now we have the differential and algebraic equations of the block number 1, block number 2, block number 3, and finally block number 4. Now, when we are in this location, when we are here, the final step is combining those equations, ordering or sorting those equations, and from there define the coefficients matrix A, B, Z, and now what you need to do is basically combine those equations, differential algebraic equations, combine them, and identify the coefficient matrices A, B, Z, and D. And to do so, of course, you need a lot of paper and a pen and some time, of course. But when you do that, you obtain over here the state matrix. The state matrix in this case is a 4x4 matrix, and it's clear. It's a square matrix, and the dimension of this matrix 4x4 is because we have 4 states in this model. And then we obtain here the matrix B, Z, and D. When we put together, you can see the full state space representation. Matrices A, B, Z, D, the clear state vector, input vector, and the output. Here is quite interesting. The state matrix is quite used. It's basically used for small signal stability for the power system analysis guys, but it is also a lot with A, B, C, and D for the control people to do the magic and to improve the response, time response, frequency response, etc. of the systems, okay? Something that I want to point out over here, if you remember a few slides ago, the block number 1 has two possibilities of representation. Realization 1 or realization 2. So if you decide to use realization 1 or use realization 2, at the very end, you will obtain a different, a state matrix that looks different if you use realization 1 or you use realization 2. For some people, they will say that those matrices are not identical. And when you compare number by number, you will see, no, they are not identical, but those are equivalents. So my job in the next video is to teach you, to show you how to use this state matrix for very useful calculation. That's all for today. Thank you very much for watching the video, and I will see you at the next one. Bye now.